Welcome back, everyone. I hope you had time for some refreshment. And we've got two talks in the final part of our session. So it's a pleasure to firstly welcome our first speaker, which is Elie LEROY. So Elie, if you want to share screen. So Elie LEROY is from CEA Saclay and is going to talk to us today about learning-based models for gravitational wave analysis.
Okay, so thank you for this introduction. So I'm Elie LEROY, I'll be presenting learning-based model for gravitational wave analysis. It's the preliminary works done in my first year of PhD at Saclay with Jérôme Bobin and Hervé Moutard. And so I'm not on the right. Okay. So I'll be presenting. So I may skip over the context of LISA because I guess most people at this attending this talk know much more about LISA than I do. But I'll just go fast on it, and I'll focus more on the problem formulation of unmixing signals in the context of so LISA data and gravitational wave analysis for LISA, and the solution proposed, which is which uses a method called the interpolatory autoencoder, which is a learning-based method that can be used to reduce the dimensionality of some problems, and I'll show how. And the results it gives in data extraction and detection criterion. And so then I'll conclude and present some perspective on my work and on my current and future work. So gravitational wave detection, as I said, I'm not going much about it, but so data is going to be complex with very high dimension signals, and so it will be useful to have some way of reducing the dimension. So the sources, there are multiples. In my work, I've been focusing on massive black hole binaries to actually complement a work done previously by Elie, which was a previous PhD student who defended earlier this month, who worked on galactic binaries. It's also interesting to know that there are other sources, and for instance, for extreme mass ratio in spirals, we don't have yet some very efficient generative model, which can also give weight to methods that don't use parametric model to be used. And so also, as Tyson presented yesterday in his talk, one of the interesting parts of massive black hole binaries and galactic binaries is that they are highly uncorrelated, since massive black hole binaries exist, are mostly stand out in time domain or time frequency domain, and the galactic binaries stand out in Fourier domain. So this is the Sangria data challenge that Stas presented earlier in his own talk. So basically, there are the chirps and there are the horizontal galactic binaries with the instrumental noise behind. So it's the same plot with only different colors. But it illustrates how unmixing can be a complicated problems in the context of LISA. So unmixing problems relies on finding some uncorrelated representation for every signal. So So basically, you want to have something that can make the MCMC stand out, the MBHB stand out from the galactic binary, from the GBs, and the other way around. So in the state of the art, most methods rely on, currently most methods are parametric methods, which use Monte Carlo Markov chains, which provides the advantages of being physically relevant, giving the actual physical parameter of the system, and also enabling the exploration of the parameter space, and providing some uncertainty quantification by giving boundaries and some insight on how the error propagated in the results provided. But they have a major drawback in that they are very costly, since they rely on multiple calls to the generative models, and so generative functions that can have a high computational cost. And especially for, so for instance, the possible tens of thousands, the hundreds of thousands of parameters that will need to be evaluated, since one massive black hole binary is described by 16 parameters, and one galactic binary is described by 8. So another way, which was presented by Sai and Tani before, is so our non-parametric method. So for instance, the principal component analysis or wavelet transform decompositions, which are actually ways to have a lower dimensional representation of the signal. So they are fast and they don't rely on generative model. Well, they are fast because they don't rely on generative models. But one of the limits of those methods is that they are linear with respect to the input signal. So they can't have the flexibility that will have nonlinear methods. And so that's where our approach inserts itself in this context. Our goal is to learn low dimension nonlinear representations of the signals to have actually to have the advantage of the non-parametric methods, but going one step further by having something that can be better at actually extracting the signal, and that sticks closer to the signal than taking a linear model. So low dimension representations, so as I said, are well adapted for so high dimension problems. Well, which is the case for ELISA, because one signal is tens of thousands. One signal can have a high dimension, which are described by few parameters. So 16 and 8 is pretty low compared to the number of observations for each system. And so actually it's a way that it's a useful tool to tackle multiple problems, because once you have a good representation of the system you want to model, you can use this representation to do multiple work. So for instance, detection, extraction. So for unmixing, it's also important to have a way to have different different representation for each system. So previous work was done on galactic binaries, as I said. So here there's the article, one of the articles she published that can be found here. And so our objective now in my PhD is to moving on to MBHBs. So the method that I used was based on autoencoders. So this is a quick overview of what an autoencoder is, but don't worry if you don't know about it, because I'll go further into it for the 3 next slides. But so it's basically a way to use neural networks to reduce the dimension of the data. So my work has been focusing on a method that's called the interpolatory autoencoder. So it relies, as most autoencoder, it relies on dimension reduction using neural networks. And so in this case, it goes from the observation that the data exists on a low dimension manifold, which is immersed in a high dimension direct space. So observation space, basically. It's the number of the direct space is the dimension of the direct space is the number of observation or measurements you did with your instrument. And so each signal can be represented as a point in this on this manifold. So A1, A2, and A3 are called anchor points. They are basically pure signals that, so in this case, pure MVHBs, not contaminated by noises or galactic binaries. They are what we want to have as the output. And the XIN, which will be the input of our autoencoder, is this is a noisy signal, and that's why it doesn't exist on the manifold. It's a bit off from it, and we want actually as a denoising process to put it back on this manifold. And so A1, A2, and A3 are called anchor points, which will be used to have a vision, an estimation of this manifold using some interpolation on them. So from this direct space, there is an operator phi that's which will be a neural network which goes into a latent space in which the signal is much more ordered than in the direct space. In the direct space, the manifold is complex. In the latent space, we make the hypothesis that it's flat, purely flat. It's an affine plane. And so in this affine plane, we can actually project which we know from the transform of the anchor points. We can project the transform of our input, which was noisy, onto this affine hull from the anchor points. And so this projection can be made orthogonally, which will be the fast interpolation, which is just an orthogonal projection onto this affine space. Or it can be done a bit more smartly by using a barycentric span projection, which will try not to minimize the distance in the latent space, but trying to minimize the distance in the direct space. So after that, there is a decoder part. So phi was the encoder which went into the latent space, and psi is the decoder which goes back into the direct space to give us a signal that we can use And so basically, phi and psi are both learned simultaneously by minimizing the function that's below. So one is so there are two terms in this loss. One is that we want x in the input and the output to be close one to another, because so it's unsupervised learning. We don't need to add labels to our data. We don't need to know what's in our data, but we want actually that after it went all this in all this, it comes back close to what was inside of it. So for the training part, of course, during the training, but we also want that in the latent space, all the training data are close to the manifold generated by the anchor points, because this means that we have something that's actually flat and not just supposed flat without having much to justify it. And so this is the minimization we do to train our neural network. And after it's been trained, we can use it to actually denoise and to represent in a lower dimension the data. So for the implementation, the encoder and the decoder were convolutional neural networks, which gives a bit of a tricky part where we need to introduce lateral connection to actually have the training part. But so there were 5 layers convolutional neural network. So it was not a big, it's not a deep neural network. It's a pretty small one compared to what can be found in the literature and in some huge tech company which have high computation power. And so it's actually, I think it takes a few hours to train. So it was trained on the 1,000 centered massive black hole binaries taken, so 500 points at sample at 5 seconds. So it was 2,500 seconds around coalescence. And we took 30 randomly selected anchor points in the training data to model the signal, and it was tested on 250 massive black hole binaries with different noise levels. We tried extraction and detection to benchmark our method. So for signal extraction,
you have about 2 minutes left, Elie.
Okay, yeah.
Thank you.
So for extraction, we just it was just taking the output of the neural network, and we see that actually it helps to denoise the signal. So this is the same MBHB in each column, but so for fast interpolation and for barycentric span projection, but also with varying noise levels. And so we see that the higher we go, the best we are, with actually a plateau which is reached because the lower dimension actually blocks the performance at some high SNR values. And so for the detection, we tried hypothesis technique. We used hypothesis testing. We generated noise only and noise plus signal models. We tried to put it into the IAE, and then we measured. So in this case, the SNR of the output. So the signal to noise ratio of the output of at the end of at the end of the IAE. And so by fixing the thresholding, because we knew for the false positives, because we had some what the outputs for noise only, which gave us the idea of how noise propagated into our autoencoder. We could fix a false positive rate, and then they say that everything that's below is can be considered as compatible with noise, and everything that's above is not compatible with noise, so should be signals. So this we had some good results on detection. And so to conclude, so this was preliminary results on MBAP analysis for LISA data using a convolutive interpolatory autoencoder. It permitted to have extraction and detection of the signal around coalescence. And so for my ongoing work and perspectives and my current perspectives, so it's I've been working on extraction during in spiral to go further before the coalescence than only 2,500 seconds. So also to have a full unmixing pipeline, we need to combine MBHB representation with galactic binaries representation to, well, for instance, tackle Sangria data and compare with, finish the comparison with PCA and wavelet transform, which are used in other parts, well, in state of the art. So thanks for your attention, and if you have questions, I'd be happy to answer.
Thank you, Elie. Very nice talk. So already there's a question in the chat. What's the dimension of the latent space? So could you answer that?
Yeah, so the latent space in our work is the same as the direct space. The transform does not reduce the dimension. Phi does not reduce the dimension. It just rearranges it, and then the dimensionality reduction happens when we project onto the affine space generated by the anchor point, which is then of dimension 30 in my work.
Thanks, Elie. Are there other questions? Okay, well, maybe I could ask one. I guess it's a proof of concept study and very nice. And could you say a little bit more about the training set that you use? So the question I have in mind is, do you have any sense of the usefulness of the method for different masses of massive black hole binaries? You know, did you consider a range of masses in the training?
So currently we've been working with masses from, I think it was 10 to the power 5. So chirp masses of between 10 to the power 5 and 10 to the power 7, if I recall correctly. And so actually, yeah, in this work, I've been working with only 2 parameter shifting, chirp masses and mass ratio. Okay. And the mass ratios were between 1 and 10, I think. Yeah, 1 and 10. Okay. And so there's the question is, well, one of the question we had was, what would it be interesting to train different models, like to have different, well, auto encoder and decoders for different ranges of chirp masses, because we know that the signals can vary greatly between one and the other. So it's one of the questions we're currently discussing.
Okay, good. Yeah, that was one of the reasons for my question. So I'm glad you're looking at that. John has a question.
Yeah. Okay.
Yeah, thanks for the interesting talk. So it's along the same theme. There's been quite a lot of work in the context of ground-based detectors on reduced bases representations of waveform models. And the equivalent here is the dimensionality of your anchor point space, I guess. So
Yeah.
how did you choose 30, or did you try different values and this one was the smallest that worked, or did you just pick 30 and then?
That's a very good question. So actually, the anchor point, we don't yet have a foolproof strategy to choose the anchor points regardless of the problem. So for the galactic binaries, what was done was that they had so they could choose a lot and then reduce by applying, for instance, some sparsity constraints, and reduce the number up to a lower number, which was so the best anchor points from the big sample they had at the beginning. In my case, we tried to do that at the beginning, but it was not very useful because we witnessed that not every with one set of anchor points chosen, not every massive black hole binaries was using the same. Well, all the anchor points were actually used. The less you have, the lower the dimension, but also the more you risk the more you will lose information. So maybe to have an idea of the number of anchor points we can go to, it could be interesting to have, for instance, some kind of PCA or some kinds of other mean of knowing what kind of order, what kind of number of anchor points we want to have. But so yeah, there's that, and there's also the possibility to use anchor points which are physically relevant. So for instance, taking some extreme values of the parameter space that we had in the beginning. But yeah.
I see. Is it just a coincidence that it's approximately the square root of the size of your training set?
Yes.
Okay.
Okay.
Thanks.
Right, well, thank you. I think we need to move on, but thanks again for a very nice talk, Elie. Let's thank Elie again. And that brings us next then to our final talk of this session, which is by Stefan STRUB. So I'll invite Stefan to share screen and then we'll introduce him properly. Okay, so it's a pleasure to welcome Stefan STRUB from ETH Zurich, and he is going to talk to us about accelerating parameter estimation of galactic binaries in the full LISA frequency band using Gaussian process regression.
Hi, everybody. Thank you, Martin, for the nice introduction. Yeah, exactly. I'm talking about accelerating the parameter estimation using Gaussian process regression. And here you see like a neat picture of LISA. So whenever LISA will be in space, we need to have tools on how to analyze the data set. And yeah, we already had a lot of talks by Tyson, Stas, and Michael about what the LDC is and what the galactic binaries are. So yeah, I can skip all this introduction a bit. So this will be how the data set will look like, a snippet of it in the frequency domain. Here we see one of the TFDI components and the data in black. And in gray, we have all the injected signals, which are within these frequency band. So here we see all these dots, which are injected, about 20 signals in here. And the goal is like to extract as many data as possible. And how can we do that? We can do that by having like, okay, we have a function with which we can simulate the LISA response. So we can put in a parameter set of 8 parameters for galactic binaries, simulate the signal and compare it to the data D. And the better the match, the better is the value of our log likelihood function. So in the end, we can have an optimization problem where we want to optimize this likelihood function, which then gives us our best match. So one way is to do that by doing it with a best fit. So we're only interested in the best fit of the data. So we can do that with differential evolution. Then we need like around 20,000 function evaluations of the log likelihood functions for that. So it's rather fast, but we do not get an uncertainty estimate. On the other hand, when our goal is to have a Bayesian posterior distribution, we can do that with a Markov chain Monte Carlo method, but this is rather slow, where we need like a lot of function evaluations in order to compute that. But on the other hand, we get our uncertainty estimate, which we like. So my goal here is now to convince you that there is a way that we can combine the best of these two worlds, where we take the result of the best fit and use that knowledge about this result to speed up the computation of the posterior distribution. So how can we do that? Here we start with a simple case where we have the data with noise and one injected signal. The injected signal is shown here as a gray line below the blue line. And when we throw the differential evolution algorithm on it, we get this blue line, which is overlapping very well the injected line. So we're happy about that. And this MLE, the maximum likelihood estimate, looks in the parameter space like this as a green dot. So this is now shown in the sky location only, but it actually is in 8 dimensions. And now we want to go from this dot here to our posterior distribution on the right, because that gives us our uncertainty. So we can do that by reducing the parameter space around the MLE, because we know like we're actually only interested in this reduced parameter space. By taking the inverse of the Fisher information matrix, we get an estimate of our uncertainty distribution. And when we take for example, the 3 sigma boundary around this MLE, we can say like, okay, we're quite confident that our posterior will lie within this region only. As you can see here, these 2 red boxes. And then what we can do then is to just sample a million times within this box with Metropolis Hastings algorithm. And what we get is this posterior distribution. But this takes a long time. It's like takes hours, and yeah, it's long. So we can speed up that process by using Gaussian process regression, with which we model the log likelihood function in this reduced parameter space. So we have like around 1,000 or 2,000 training samples within this 8-dimensional reduced parameter space, train our model, and then we can evaluate that log likelihood function quickly from our model. And that then gives us our posterior distribution with millions of samples within minutes. So that's very nice and very much of a speed up. So again, as we see, like we have a single signal, we get a best fit. From the best fit, we get a posterior distribution, all nice and neat and fast. But maybe you're not convinced yet. Maybe you say like, this is only a single signal. What about overlapping signals? Here we go. This is now 2 signals. The first signal, as just shown before, the blue one is still here. And now we added a second one. So what happens when we throw the differential evolution algorithm on it? We still found the blue one, but it's a bit different. It's like there's a bias induced from this secondary signal. And then as the red line, we have the residual, where we say like, okay, we subtract the blue signal, which we found from our data. And if we look at, okay, it doesn't look like it's on noise level. It's like still there's something in it. So it's like, okay, let's run it again. Let's throw the differential evolution algorithm on it again and see what happens. See here, we find this orange one. So, okay, how does that look like? Let's subtract both of them from the original data and see what happens. We see like, okay, this red one still like, there's still a bump in it. It doesn't look neat. And also the blue one doesn't match well. So the bias is there. So what can we do? We can do a global optimization with these 2 signals here as an initial guess, because the thought is that like, okay, these 2 initial guesses are actually quite close to the global mode of like these 2 signals together. And we can do that, and we see now, oh, hooray, the blue one and the orange signal, they're actually matching quite well. And our residual is actually at noise level. So we are very happy about that. And does this also like get rid of the bias for the posterior distribution? Now shown here is the posterior distribution. The blue one is the same one as shown before. And the red one is now the posterior distribution of the first signal, still the blue one. But initially the data contained both of these signals. And then when we subtract the orange one from our global fit, we see like, okay, that our posterior distribution has the bias quite remarkably removed, especially in the sky locations and frequency derivative, not as much in the amplitude and inclination, but they're still like good overlapping. So we are happy about that. So this is an example of two signals, and they were like quite in the middle of the window we set, but what is like the whole LDC, like the LDC14 with like 20 million signals in it. Okay, let's look at a section of that where we say like, okay, we have 4 of these windows split by these red lines. So like we have this first window would look data all the way to this neighboring middle line. So it would receive data all to there, but it would only accept signals which are within this blue region. And the same goes for this one. So let's call these blue ones odd windows, and these neighboring in between the odd, these are the even windows and these are the odd windows, right? So let's throw our algorithm onto the even windows and see what happens. Okay, we see we have a green result, blue, and the orange one from the first one, but only the blue one is within the shaded region. And on this side, we have the red, brown, and the purple one. And then we also have this gray one, which is coming from the signal all the way to the right, from the window all the way to the right, which is actually not plotted. But we see like, okay, we're not interested because these are plotting the same signal twice, but it doesn't matter for us because we're neglecting that. We're throwing it away. We're only interested in this red one and the blue one. So what we can do is we subtract these two signals and we get the residual shown in the CN, and then we can throw that again into the odd windows one and repeat it. So now we get all these signals. We only have, we only have this one orange signal, which is outside of the windows. All the other ones we accept. And now let's repeat it again with the original data. And now we see, okay, let's do the evens again, where we subtracted the odd signals we found in the odd windows. And let's see again what happens. Okay, we get this orange, blue, the green, and the red. So we're happy. We can combine all these together, and this is what we get. We find all these signals, even like in this like huge overlap, we get a lot of signals out of them. And in total, we find 14 out of 20 of these signals. So yeah, this is all about the method. But now let's talk about like the performance. Let's talk about numbers. We like numbers. So if we do that for the whole Radler data set, 1.4, then there are like 26 million signals in there. They're like a lot. So we restrict ourselves to 0.3 millihertz up to the Nyquist frequency. 0.3 because here is like even the instrument noise is like higher than most of these signals. Like there's not much use of going lower than that. And in this region, we have 6.8 million signals, which are quite a lot. And we're not expecting to get all of these since like most of them have like a super low SNR. So let's say like we are only looking at the ones which have an SNR above 10. So they're like about 18,000. So like that sounds realistic. So let's look what the pipeline throws out, and we find almost 19,000. So a bit more even than we expected, which is quite nice. And let's see now how well do they match. Like does like these signals which we found, does it have a companion of the injected signals? And we can check this companion with the correlation function down here. If we say like the correlation is above 0.5, we accept it as a match. It has a companion which was injected. And we see that we have 16,000 of these got matched, shown in green. And we have 2,000 of these which are ambiguous. They don't really have a companion. They're not matched. And in the end, we get a match rate of 88%. So 88% of all the found signals are matched. And here now in red, I'm showing you the injected signals which do not have a match. And now this plot is interesting because we can see like, oh, okay, all these loud signals, we can match them well. Down here, no chance. And here in blue, we have a confusion cloud where like a lot of signals are overlapping. So like most of our like ambiguous signals are over here. Then here we also have a region where we have these two highest frequency ones did not get a match. Why is that so? There's actually, the reason is for that we plot it, when we plot it, in black the data, and in gray we have all the injected signals in there, like given from the parameters from the LDC, from the data challenge. We see that it actually does not match the data. So we do actually expect that the signals we're finding, which are trying to match the data, are not matching these parameters of the injected signal. And this as well for the second highest frequency. So we are actually not concerned about these. We're actually happy that these two did not match.
You have about 2 minutes left, Stefan.
Yeah, thank you. So now let's talk quickly about computational time. So yeah, there was a question before from Jean-Baptiste, and I have some answers, like how long it took for me. So the even one where we restricted the first one up to 3 signals, it took 1,500 CPU hours, the odd ones 3,000, and the even ones 2,400. And in total, we get about 7,000 CPU hours. And the good thing is now that we can actually parallelize this whole thing. So this is all like these have not neighbors like which are connected. So if we have a CPU, like if we have 3,485 CPU kernels, we can run this all in parallel, and then we would get computational times of about 27 minutes. So in total, all that together, we have 2 hours, and we get this signal, like all these found sources, which is quite nice. And then we can also do that for half a year of data. Just now it was always with 2 years worth of data. Now you can see if we switch forth and back, the cloud actually is moving down when we're going to half a year. So the SNR is getting lower. So we're actually expecting to find less signals now, 6,400. And we got about 8,000, and we have quite a good match rate of 91%. So this is quite nice. And to conclude is that, yeah, we have, I hope I convinced you that there is a way where we can have a Bayesian parameter estimation as soon as which is fast, as soon as we have like all the signals in there which are loud. If we match them quite well with the best fit, we can subtract them, and just with the remaining one, we can quickly get our Bayesian parameter estimation within minutes. And we can also all like parallelize that. We have a robust pipeline to extract the galactic binaries, where we find a lot of signals within the 2 years worth of data. We have low computational costs. Also the low latency, because we can parallelize it. So the full galaxy we have within 2 hours. And it can also be time evolving, or like it is actually in time evolving, where we say like the previous searches, signals, we can use them as initial guess for a later stage. And that further speeds it up. And yeah, I'm happy to take questions.
Thank you, Stefan. That was very nice. So as Stefan says, are there any questions? Looks like we have a hand up, and that is from Jesus. So over to you.
Hi, Stefan. Very, very nice. Oh, sorry. Hi, can you hear me now?
Yeah.
Yeah. Very, very nice talk. I'm working on Gaussian process regression applied to Bayesian estimation in a different field, not in gravitational waves. And I was wondering, so for us, getting a Gaussian process to actually converge and reproduce the distribution that we are looking for is not trivial. And definitely not trivial for, do you have like 6, 7 dimensions?
8.
8 dimensions. So do you find any problems there, or with your 1,000 or 2,000 samples always converge precisely?
So what I'm doing is I start with 1,000 samples, and if I don't, I have like 5,000 which I test my model with, and if I don't have a good RMSE, then I get like if I have a high error, then I repeat it again with 2,000 more, and repeat it again up until 4,000. And usually within 4,000, I have good accuracy.
And I reckon you're using something basic like Scalar, basic, not in the bad sense, but I mean not using CPU, for example, like Scalearn or GPy.
No, it's all on CPU. Actually,
it's on CPU. So it's a Gaussian process with 1,000 samples is not very fast to evaluate, right?
It was okay. I did it with scikit-learn.
Yeah, I also use it.
There's like 1 microsecond or so for if I have 1,000 training samples.
Okay. Well,
yeah.
Okay.
So just one suggestion, like I think it's important. You have if you're using Gaussian processes, then you can get the derivatives for free. So maybe you want to swap your MCMC on the Gaussian process by, for example, Hamiltonian Monte Carlo, and you can actually converge with many fewer evaluations. Just one piece of advice.
Thank you.
Okay.
Yeah. Thanks. Interesting. So let's go to John now.
Hi, Stefan. Thanks for the nice presentation. I noticed that you had a number of sources that were found but not matched that had quite high SNR.
Yes.
Do you understand what they might be? I mean, it looks in this figure, for example, that those 2 injected not matched sources at high frequency might have just been split up into a bunch of lower SNR sources. Does that explain some of the others as well?
Yes. So, for example, where you have like, it's not always perfect. So like, for example, rather these ones, which have a pair with an injected, which is not matched, there you can say like, actually the differential evolution algorithm is not perfect, right? It's like, it has like a match, a success rate of like 90%, let's say. So I'm actually repeating it 3 times for each signal. So there, with that, I get a like success rate of 99.9%. So out of still like 18,000 signals, I still expect that I get 18 signals which are not perfectly like finding the best fit. So this is it for these pairs. For these, yeah, it's like a bit like you said that there is getting something is matched. Like there's also like with noise, there's something like it can build up. Actually the match is way higher. So the match gets a way better SNR than the actual pair it would get. So also just the amount of signals can by coincidence build up a signal which is not there.
And is there any way to diagnose that that's happening, or is it just something we have to live with?
I don't know yet. Well, okay. It's definitely, you can say like, okay, in this like low SNR region with at this frequency where we have this confusion cloud, you have a higher chance of being ambiguous. So there you can even say like, okay, like this is like the ratio of being ambiguous, because yeah, we don't know it with the real data. But up here, you could be saying like, okay, I'm quite confident because like 99 out of 100 signals are good. So with this simulation, at least.
Okay, thanks.
Yeah, welcome.
Okay, thanks, Stefan. So we're a little behind schedule, but it was an interesting discussion. Seemed a pity to cut it off there. Let me just check. Are there any final questions? Time for maybe one more. Well, let me just ask one, which I'm curious about. So your matching criterion is a correlation coefficient of greater than 0.5. So how does your matching rate depend on that choice? If it was, for example, 0.6 or 0.7, how would that change the matching rate?
Yeah, if it would be higher, the matching rate is better. It's higher, but I would, yeah, definitely also get more rid of these like 16,000. It will go lower.
Yeah.
I actually have a histogram plot right here ready. So here you see the histogram of the correlation. So you see like most of the signals live up here. So if I say I would cut it off at 0.7, for example, I would get rid of like 1,000 signals which are living down here, but I get a better match rate.
Yeah, I was wondering, as John asked his question, whether the variation with the correlation coefficient might be some kind of diagnostic tool for, misclassifying. I don't know, but it would be an interesting thing to discuss more. Anyway, let's thank Stefan again, first of all, for a very interesting talk. And let's thank all of our speakers and indeed all of our audience for sticking with us. I think there's a final talk just going on in some of the other sessions. You're welcome to join that if you have time. And of course, don't forget to join us again at 11 o'clock Central European time tomorrow morning for our next plenary session. So with that, I will sign off and thank everyone again.
Thank you.
Bye-bye.